Welcome back. So we are working on today's lesson, chapter 12. We're going to continue talking about the atmosphere, and this time we're taking a look at clouds and precipitation, and so that role of water, the ever important role of water in the Earth kind of atmosphere system, Earth as a system. And so chapter 12 we're going to devote to clouds, but really kind of how we're getting clouds in the first place. So the stability within the atmosphere, we'll be taking a look at that, how precipitation actually does form, various types of precipitation, measurements that we take of the precipitation. And so let's get started with water, okay? How that plays a role in our atmosphere, a very important role in our atmosphere. And so the changes of state of water, okay, of course that exists as a solid, a liquid, and gas or vapor in the Earth atmosphere kind of system, ocean as well, right? But we're focusing in on what's taking place in the atmosphere. So those changes of state of water, going through physical states of change, is going to require some heat energy. Not that we're actually changing the, say, temperature of the water so much, it's that there's energy going into creating the change of state. So say going from a solid to a liquid, you're going to have an input of heat energy to get that transformation from solid form to liquid form, and going, say, from liquid form to vapor form. You're going to have to even put more input of this heat energy in order to get that phase change of water, of any type of matter, but in particular we are talking about water here. So that heat energy gets measured in these units that we do call calories, and 1 calorie is the heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, that's what a calorie is. Now, we mentioned this term latent heat. I kind of think I wrote it up on the board in the last chapter, but it's really talking about it here for the latent heat. This is stored or hidden heat. We can store it or we can release it actually, and it's not derived from a temperature change as that's noted in there. It's not really changing the temperature of the water, but this energy is going in or being released, we'll look at that as well, to account for these changes in physical state, to bring about a physical change in state. So this is a very, very important in the atmospheric process, as we will see. But that's known as latent heat, latent in that it's kind of this hidden heat, they say. So latent heat brought about by the physical changes of state in our water changes. Okay, so of course those 3 states of matter, of water, solid, liquid, and gases. So to change that state, we've got to either have heat being absorbed or released. So in order to change state, let's just think about water, the water molecules. So in a solid state, you have a very dense and compact arrangement of the water molecules, kind of a rigid compaction of those water molecules. As you go to solid to a liquid state, those water molecules are starting to move around more. And so you've got to add some heat energy to get that motion, that movement of the water particles. To go from a liquid state to a gaseous state, well, in a gaseous state, those water molecules, are really bouncing around and zipping around. That requires even more energy, the input of these calories. Now, if we were to go back the other way, so from a higher energy state to kind of a lower energy state, going from vapor or gas back to a liquid, well, all that energy we had put into to go to the vapor state ends up getting released when we go from the vapor back to a liquid state. So it can either be absorbed or released, those heat kind of calories, that energy, to bring about these phase changes, these physical state changes of water. And so this is what we'll be looking at here through those processes of physical changes. So here's the processes. We're going to talk about each one. There are actually 6 processes in the physical changes or states of water. The first one they talk about is evaporation. So this is when liquid water is going to be changed into a vapor or a gas. Okay, so liquid to gas, that's evaporation, a very important process. For that, just to kind of round the number off there, we need 600 calories per gram of water need to be added to the system. We're going to go from a liquid to that very high kind of velocity of the gas molecules state. So we need to add some energy in by the amount of 600 calories per gram of water. This is called the latent heat of vaporization. So evaporation, going to a vapor. We got to put an input of heat energy. Condensation, kind of going back the other way. Here we're taking the water vapor, the gas form, gets changed back to a liquid. So all that heat energy we added to become a vapor, that is going to get released. Those same 600 calories, right? The 600 calories is going to end up being released. Okay, so the heat energy is released. That's called the latent heat of condensation. So here we're going to a little more compact arrangement. We don't need all that heat energy. It ends up getting released in the condensation process. Okay, there's 2 of them. Next one, melting. I'm sure you've heard of melting. It might only be a couple of these you might not have heard before, but melting. Here is where we're going solid to a liquid state. Okay, that's melting. For that one, we don't need quite as much energy. We're going from solid, very dense arrangement to this little bit looser arrangement of molecules. We only need about 80 calories per gram of water that need to be added to get it to go to that liquid state. So that's melting. That's called latent heat of melting, latent heat energy. Freezing, on the other hand, the liquid going back to a solid. Well, we don't need all that energy. Now our molecules are more densely arranged, more static. In there, we release that energy. So those 80 calories get released. The heat is released. That's called the latent heat of fusion. We're kind of fusing to a solid state in there. So there's 4 of the processes. Now here might be a couple that you haven't heard of before. This process of sublimation, maybe you have heard this one. This is where you go from the solid phase directly to the gaseous phase. You kind of skip the liquid phase altogether. You go from solid to gas. For that one, you're going to need quite a bit of energy. In fact, it takes 680 calories per gram of water to be added to go from a solid directly to a gas in the sublimation process. If this is something, maybe you've witnessed it before, but this is like ice cubes shrinking in a frost-free kind of freezer compartment. If anyone makes their own ice cubes anymore, you set them out in the trays, right? And over time, if no one uses up the ice, over time it seems that those little ice cubes are shrinking in your freezer, and that's what's happening. You're going through solid state directly to a gaseous or vapor state of your ice cube in there. So that's a good kind of scenario for sublimation. But that's going to take 680 calories, because remember, going from a solid to a liquid took 80 calories of energy input, and then from liquid to vapor it took 600. So if you combine all that, that equals 680 calories. So it makes good sense of what has to be added in order to go from solid to a gas. Those 680 calories of latent heat energy added. Okay. Deposition is the opposite of sublimation. So this is where you're going from gaseous or water vapor to a solid. Okay, so water vapor gas change to a solid. Heat is going to be released, and it is going to be in the amount of that 680 calories. We will see. So all of that got put in through sublimation gets released during a deposition process. So those are your 6 states of processes that water will go through those different various changes of physical state, going from solid, liquid to gas, and back and forth throughout. So here's a nice diagram. Let's see if we can get it all in the picture here. Yeah. So changes in state of water. They actually forgot one on your PowerPoint. I went ahead and wrote it in, one of the processes. But if we look here, we can kind of see the solid water, so the form of ice, very densely arrangement, very compact arrangement of the water molecules in your solid phase. Those particles are not moving very rapidly at all. And then coming here to the liquid water stage, we're starting to get some motion of those water molecules. Over here, you're seeing those water molecules kind of zipping around in the gaseous or water vapor state. So the physical states, changes of water, and then those processes we talked about. And so this kind of color coded, I don't know how well that's showing up for you in the video, but these ones with blue, okay, that is where we are releasing energy to the environment. We're releasing that latent heat to the environment, the little blue code. The red code means all of these color coding here for red processes means that energy is being absorbed. The latent heat energy is being absorbed from the environment to achieve those physical state changes. And so if we look here at melting, we're going from solid to the liquid phase, right? The melting. You're going to have an input of 80 calories, as we mentioned before, to achieve that process, that physical change of state. If we were to go to liquid to water vapor, right, gas, that's actually called evaporation. They left that off in your PowerPoint, so you might want to fill that in. Evaporation is that process. And I know they have 540 to 600, but we're going to keep it simple and say 600 calories. That'll make it easy to remember for that. So that would be an input of energy that we would need from the environment, absorbed from the environment, to go from liquid to the water vapor or gaseous state. And then that third one that required some absorption of latent heat was going from a solid directly to a gas. And so solid directly to gas, that's that term sublimation. And so that actually does need 680 calories. Remember, 80 from there to there, and 600 from liquid water to water vapor. So a total of 680 calories needs to be absorbed, latent heat absorbed from the environment, in order to achieve a sublimation process, going from solid to gas. Then if we go back the other way, so here we're going from a higher energy state down to a lower energy state, we're going to be releasing some of this energy. So going from a gas, okay, to a liquid, that was known as condensation. So if it took 600 calories to go from liquid to gas, well, when we go from gas back to a liquid, we end up releasing those 600 calories of latent heat back to the environment. And so that gives us condensation, gas to liquid. You see, that's a release of latent heat to the environment. To go from the liquid state to the solid state, right, that's freezing. That's going to give off another 80 calories, okay, just a little bit more of that latent heat being released back to the environment when we're going to a lower energy state in that process of freezing. And then we had one more that we talked about, going from a gas directly to a solid, so deposition. That's going to be a combination of the 80 plus the 600. So 680 calories gets released back to the environment of that latent heat energy, that hidden sort of heat that they talk about. Okay, and in calories are the units. So those are those processes. You want to make sure that you Study that really well so that you do know those phase changes, all 6 of them. Well, all 3 phase changes, but all 6 processes of going through the various phase changes of water. Okay, and the number of calories that go with each of those. Okay, so change the state of water. Latent heat, either absorbed or released. Okay, and just kind of remember your amounts that go with those, each one of those processes. Okay, so again, looking at the amount of water vapor in the air, this was called humidity. We did kind of introduce that term in the last chapter when we talked about the elements of weather. Humidity was one of them, and that is something that, of course, meteorologists do talk about every single day in their weather reports, but it's the amount of water vapor, so in the vaporous state, the gaseous state, in the atmosphere. Okay, so water vapor in the atmosphere, and this was a variable amount. If you remember our talk last time, it can be up to 4% of the volume of the atmosphere, but that's going to vary. So saturated air is air that is filled with water vapor to its capacity. We are going to find that the capacity of the amount of water vapor that the atmosphere can hold, its capacity, is temperature dependent. Okay? Warmer temperature atmospheres can hold more water vapor. Colder temperatures can't hold quite so much. And so that capacity, what your atmosphere can actually hold, is temperature dependent. It will change. Its capacity will change depending on temperature. So warm air has a much greater capacity to hold, we would say, water vapor. Okay, so water vapor does add pressure to the atmosphere. Remember our mixture of gases, mostly nitrogen, right? We've got some oxygen in there, argon, and some other trace gases as well. Water vapor could be part of that. Well, water vapor does add some pressure, and so that portion of the pressure is called vapor pressure. It adds a little pressure to the air, and so water vapor is called vapor pressure. So capacity, let's think about that. How much water vapor can the atmosphere hold? It's going to depend on the temperature of your atmosphere, as we're going to see. Okay, something called the mixing ratio. I'm trying to measure humidity. It's an important element in weather. But mixing ratio is the mass of water vapor in a unit of air compared to the remaining mass of dry air. So many grams of water vapor per kilogram of dry air is what they usually use, the unit, grams per kilogram. So the actual mass in grams of the water vapor, okay, per kilogram of the remaining dry air that doesn't have the water in it. This is known as the mixing ratio, okay? And so grams per kilogram in that. It's kind of how much the atmosphere can hold. Again, temperature dependent on there. So something maybe you've heard of, relative humidity. A lot of the weather reports, the daily relative humidity will be spoken of often, every day. They'll talk about what the relative humidity is. But this is a ratio of the air's actual water vapor compared to the amount of water vapor required for saturation at a particular temperature. And so, like I mentioned, the atmosphere at various temperatures can hold particular capacity of water vapor. Okay, so relative humidity, there's a little equation for it. It's expressed as a percentage, so percentage of relative humidity, RH, times 100 to get the percentage part. But percent relative humidity is this ratio of the water vapor content, so the actual water vapor content, compared to the capacity, which is temperature dependent. So how much water vapor can the atmosphere actually hold at a particular temperature? And there are all these tables that you can look up to figure out what your capacity is. What would make that saturated for a particular temperature? So you've got a capacity. So what the actual water vapor content is compared to the capacity at a particular temperature, right? And it's, you know, for a particular temperature and of course pressure, in order to make that saturated, that would be capacity, okay? And then you're looking at, well, how much do we actually have versus what the atmosphere could hold at that specific temperature? What would be the maximum saturated capacity? This is how we calculate relative humidity, percent relative humidity. So ratio of the air's actual water vapor content compared to the amount of water vapor required for saturation at that temperature. What its capacity would be, meaning at saturation. How much it could hold, and it cannot hold anymore. And that will be unique for a particular temperature, okay, and pressure, of course. So content over capacity times 100. That's the relative humidity. So it is expressed as a percentage, but of course that's relative to temperature, so that can change with temperature. So saturated air. If you have saturated air, your content equals your capacity. That number and that number would be the same. And in that case, let's say this was 50. 50 would be your actual water vapor content, and 50 is the capacity that it could hold at a particular temperature. So 50 divided by 50 is 1. 1 times 100, 100%. So you'd have 100% relative humidity, meaning saturated. So anytime your content equals your capacity, okay, content equals capacity, you have 100% relative humidity, and that air is saturated with water vapor. It cannot hold any more water vapor, okay? So when content equals capacity, you do have a situation where you're at 100% relative humidity. Okay, so that's a little ratio going on. So how can we change up relative humidity? Well, a couple of ways, right? We've got a couple of variables here, and we can change this in a couple of ways. So one way is, well, what if we added more moisture? We added more content. Our capacity stayed the same, but we added more content, adding more water in, okay? That would actually increase your relative humidity, right? We got a bigger number up here. So we would increase the relative humidity by adding more moisture in. Okay. Well, what if we took some moisture out? So we took out some of that content. Okay, that would lower your relative humidity. So that is a direct proportionality, right? Adding water in or removing water, increasing or decreasing relative humidity. So that's one way your water vapor content, a top value, could be changed. And then the other way, of course, is to, well, change up your capacity, right? And how do we change our capacity? Is by changing the temperature, the air temperature. So remember, warmer air can hold more water vapor, colder air can't. So by changing the temperature, we actually will change up the capacity, and that is an inverse kind of relationship. One goes up, the other one goes down. So a couple ways we can do this. By changing the air temperature, you can lower the temperature. So if we lower the temperature, we can no longer hold as much water vapor. So that would lower our capacity. Okay. Well, if you lower the temperature, you're lowering your capacity on how much water vapor it can hold. Your content stayed the same there. That would actually raise the relative humidity. So you've got a certain amount of water vapor in there, but you cool that air. Well, that air can no longer hold as much water vapor, so that drives the relative humidity up. Okay, so reducing your capacity is going to increase your relative humidity. That is sort of an inverse relationship. Well, let's say if we raise the temperature, we increase the temperature. When you increase the temperature, the atmosphere can hold more water vapor, so you increase your capacity. If you increase your capacity, you lower your relative humidity. So a couple of scenarios there, increasing temperature or decreasing temperature can have an effect then on your percent relative humidity, even if the actual content, water vapor content, doesn't change. Changing the temperature changes the capacity and therefore will change that ratio for you. So that's another way, changing temperature. The other one is the actual water vapor content, add or remove. A couple of ways, okay. Dew point temperature, and that term dew point. So dew is liquid droplets that come out, right, of the atmosphere. So the dew point temperature is the temperature to which a parcel of air would need to be cooled in order to reach saturation. So the air would need to be cooled down to a certain temperature to where, you know, it has a capacity that's going to equal the content, right? 100% relative humidity, saturated, that would be a dew point. If you were to cool that down just even a little bit more, the atmosphere could not hold any more of that moisture and it would condense out. It would cause some condensation, and that could be, of course, in the form of dew, right? Liquid dew, frost, it might be fog, some sort of condensation happening if you cooled that down just even slightly under that dew point temperature. That's why it's called dew point. The air has been cooled down in order to reach saturation, okay? And that's a dew point. So that is something that really is a good way to think about the actual amount of water vapor in the atmosphere. And a lot of times you're going to see your meteorologists talk about that dew point temperature, how much the air has to cool down, okay, in order to become saturated. Content would then equal the capacity, 100% relative humidity. That's your dew point temperature. And I think they'll mention that a little bit more on the dew point. Here we're just looking at those couple of scenarios of how we're changing up relative humidity. Okay, see if I can get all that in there. But this scenario, they are keeping the temperature constant. So if you keep your temperature constant, you keep your capacity constant. That's not changing. So what they're doing is they're adding the content of water vapor, and they're doing a little change in there. So as you notice, all the temperature is steady. Panel A, initial condition 25 degrees Celsius, B 25 degrees Celsius, panel C 25 degrees Celsius. So they haven't changed the temperature at all. Okay, so our capacity will stay the same. So that capacity is called the saturation mixing ratio, right? At 25 degrees Celsius is called, or can hold 20 grams per kilogram of air. So 20 grams in each panel, that's all it can hold. So over here, they started by adding 5 grams of water vapor. So to do our little relative humidity computation, you put your 5 grams, that's the actual water vapor content, divided by those 20 grams, the capacity. Okay, 20 grams for capacity. So 5 divided by 20 is a 25% relative humidity. Okay, and that's that first panel, condition A, the initial condition. Now they're going to add an additional 5 grams of water vapor content here in this panel. So now we have 10 grams of water vapor content. Temperature's the same, so capacity is the same. It's still 20 grams for our capacity. And so now our relative humidity becomes 10 divided by the 20, or a 50% relative humidity for panel B, this one. Next thing they do, they go ahead and add an additional 10 grams of water vapor to what was already in there. So now they have 20 grams of water vapor, and the capacity is still 20 grams because they didn't change the temperature. So 20 divided by 20, content equals capacity, that equals 100%, right? Relative humidity, okay? We are saturated. The air is saturated inside of that little glass tube in there, okay, in that scenario, okay. And that was just adding some water vapor and how we were able to change relative humidity. Well, here they're keeping the content the same. They're not changing that one. Constant water vapor content, they're saying here, okay. What they're doing instead is lowering the temperature, which is going to change the capacity. The cooler the air gets, the less capacity, the less water vapor it can hold, and we're going to see what that does to the relative humidity here. Okay, so we're starting out, the temperature to begin with in the initial condition is 20 degrees Celsius, and then they're going to cool that to 10, and then they're going to cool it further down to 0 degrees Celsius in this flask over here. So the amount of water vapor, the water vapor content stays the same the whole time. It's 7 grams of water vapor per kilogram of air in that flask, in the first one. And so at 20 degrees Celsius, the water vapor capacity, that mixing ratio, saturation mixing ratio, is 14 grams. It can hold, at 20 degrees Celsius, 14 grams of water vapor per kilogram of air. That's what its capacity is at that temperature. Okay, so we have 7 grams of water vapor. We could actually hold 14, so 7 divided by 14 is going to give you a 50% relative humidity on the first panel there. Well, now we're going to cool that. Our water vapor content is the same. We still have the 7 grams of water vapor, but we're cooling it down to 10 degrees Celsius. That changes our saturation mixing ratio, our capacity, to now we can only hold 7 grams of water vapor per kilogram of air. So we have 7 grams of content, and now we can only hold 7 grams for capacity here. So 7 divided by 7 times 100 equals the 100% relative humidity. We are at saturation now, and we're going to continue to cool this down a little bit. So let's see what happens in this third panel. So we're cooling it down to 0 degrees Celsius, and at 0 degrees Celsius, the capacity is only 3.5 grams. It can only hold 3.5. Remember, we had 7 in there. So 3.5 grams. That's all it can hold. So if we have 7 and it can only hold 3, that means that another 3.5 grams has to condense out. The air cannot hold it. That's kind of it's saturated. So yeah, you're going to have 3.5 grams of water vapor in the air, okay? But look here, you also are going to get 3.5 grams of that water vapor to condense out, so back to a liquid in the bottom of your flask. The relative humidity, of course, is going to be 100%. You've got the 3.5 grams of water vapor, right, divided by the capacity, 3.5 grams. That's 100% relative humidity, but we condensed out 3.5 grams. Remember, we had 7 grams of water vapor. It could only hold 3.5, so the other 3.5 condensed out in the form of a liquid water here. We would call that dew, right? So we basically hit our dew point, right, at 0 degrees Celsius. We could not hold any more, and so that's going to condense right on out. So this would be saturated at 100% relative humidity, plus then the dew that came out, the condensation that came out. So yeah, changing of the relative humidity It's like the name says, it's relative, because it's relative to what's going on with your capacity, just temperature dependent, or maybe you're adding or removing water vapor. So two scenarios in there that we could change up our relative humidity. So actually, they do like to look at the dew point temperature. That really tells you when you're going to be at saturation. So let's say on a particular day, the atmosphere, we want to make sure we can do a little calculation for this, say on the exam. Let's say that we had the 2.5 grams of water vapor, right? So your water vapor on a day, right? Well, where the temperature was that at saturation, you could actually hold 10 grams, let's say. Make sure I got that. Yeah, 10 grams. On a particular day, we could hold 10 grams of water vapor. That'd be like the capacity. At a particular temperature that we could hold 10 grams. Well, what would be our relative humidity in this case? You would take the 2.5, divide it by 10. Don't forget to multiply by 100 because it is a percentage. You would end up with 25% relative humidity. Right? 2.5, that's what the actual content was. And what its capacity was, it could actually hold 10 on a particular day, particular temperature. So make sure that you can do a little calculation for relative humidity. We may have one of those on the exam. Okay, so just playing around with content over capacity. Try to remember that equation. Okay. Dew point temperature. So cooling the air below the dew point, right? Dew point is your saturation point. Air is saturated at that particular temperature. It cannot hold any more water vapor. If you cool that down even just a little bit more, that is going to cause condensation. The water vapor is going to condense back to a liquid. And so yeah, you can get that in the form of dew, maybe fog is happening, or even little liquid cloud droplets. Okay, so condensation to make the cloud droplets. Now, in order to actually condense, water vapor needs a surface to condense on. And so in an earlier chapter, we talked about how those aerosols, this was last chapter, the aerosols, the dust, those little solid particulate particles, the dust, pollen, soot, you know, it makes the beautiful sunsets, that sort of thing. But that is something that the atmosphere needs, right, for the water vapor to condense on, the little aerosols, to create a cloud even. So those are known as cloud condensation nuclei. They really like to kind of absorb the water. They are attracted to the water, hygroscopic little particles. So cloud condensation nuclei are required for condensation to happen. We need a solid surface for the condensation to happen. Okay, and so in order to kind of get the clouds, you do need those little particulate matter in there. I think they're going to talk about those and formally give you the name of that here in just a bit. But let's look at those variations in temperature and relative humidity, let's say over a scenario of a day and then to the nighttime kind of thing, and how that's varying throughout the day. So let's take a look here on the left margin here. We've got our relative humidity, percent relative humidity up along that column. Over here they've got two scales of temperature. Of course, this would be your Celsius here, and then in parentheses they've got the Fahrenheit temperatures, whichever you prefer there. But kind of looking at what happens as temperature rises throughout the day versus as the temperature decreases throughout the day. So the red line here is, we've got like 12 a.m. here, 6 a.m., noon, 6 p.m., and then midnight again. So throughout the day, the red curve here, as we're coming off of, midnight, and then we're getting to about sunrise here at 6 a.m. That's where you have like your lowest temperatures from all the radiation cooling that happens at night. All the heat, you know, is kind of radiating out. So you get your lowest temperatures just before sunrise, right? But because those temperatures are low, they cannot hold, that atmosphere cannot hold as much water vapor, right? That's going to drive up your relative humidity, right? The lower those temperatures, the less the capacity for water vapor, that increases your relative humidity. Just see how that's an inverse relationship. So just before sunrise, right, our lowest temperatures, but our highest relative humidities are going to happen, okay, overnight. But as the day treks on, the temperatures begin to warm and warm and warm. So, you know, along about 4 p.m. or so, we get our highest temperatures of the day. That would increase your capacity to hold water vapor. Higher temperatures, right, can hold more water vapor. That ends up decreasing your relative humidity as the day kind of goes on towards the peak temperatures. This is definitely an inverse relationship going on with that. Temperature goes up, relative humidity goes down, right? And then, of course, overnight, as the temperatures are going down, right, going down, relative humidity is increasing. So that just before kind of sunrise there, you've got your lowest temperatures and your highest humidity. Definitely an inverse relationship happening here in this scenario. Okay, so just kind of think, keep that in mind about the inverse relationship that we have. So, humidity usually increases while the temperatures decrease, and so our highest relative humidity is going to be about at sunrise, okay, when we have our lowest temperatures. So trying to get at the measuring of the humidity, okay, there's a few things that we use for that to measure that water vapor in the air. For relative humidity, and there's tables for this that we can use, but a couple types of hygrometers. So these are measurements of water, hygrometers they call them, to measure humidity. One that we use a lot, very reliable, is a psychrometer. I brought my psychrometer with me. The psychrometer compares, it actually has two bulbs. So one we call a dry bulb, so a thermometer, dry bulb, and the other one here is what we call a wet bulb. Now the wet bulb has just a little piece of gauze around it, a little piece of cloth around it, and I'm going to moisten that with some water. And then what you would do is you're going to actually swing this around, right? I'm going to get it wet first, but we'll swing it around, and then we're going to compare the temperatures of the wet bulb thermometer and the dry bulb thermometer. The greater the difference between those two values, the lower the relative humidity. So what's going on with that? Well, when I've added the moisture to my gauze here, right, I'm kind of wrapping that gauze around the bulb there, and then I'm going to be flinging that in the air like that, kind of facilitating some evaporation to happen. And if you remember, it's similar to, I don't know, if say you have a washcloth or a towel or something, maybe you're out doing sports or something, and you moisten a towel and then you swing it around in the air, spinning a towel in the air rapidly, and then you feel the towel. It's nice and cool. Why? Because that water was evaporating off into the atmosphere. Well, evaporation requires 600 calories, right, of latent heat to be absorbed from the environment. So in order to evaporate that, it had to pull 600 calories, right, of heat from the environment to cool that down. And so then you can put that nice cool towel on your neck or your forehead or something. The same type of thing is happening with this gauze here. So as I'm going to swing that around in the atmosphere, I'm facilitating evaporation. So the evaporation process requires 600 calories of latent heat to be absorbed from the environment right around my thermometer. So it actually would lower that temperature just a little bit. So you have a dry bulb temperature, the ambient temperature of the air, And then the wet bulb, what's going on with, how well is your atmosphere evaporating that water. If you have a saturated atmosphere, it is saturated with water vapor. The water vapor from my gauze here is not going to want to go into the atmosphere, so my temperature on my bulb is not going to change very much. So the closer these values are together, dry bulb and wet bulb, the more saturated you have. If these are equal, if they're the same, temperature hasn't moved at all, the atmosphere is saturated with water vapor, and I can't get any of the water from this gauze to go into the atmosphere. So what they're saying here is the greater the difference between the dry bulb and the wet bulb, the lower the humidity is. The water vapor content in the atmosphere is low, so yeah, this is fine. That water from my gauze is going to evaporate with no problem. Okay, if those are very large differences between them. Okay, so let's just see here. I've got a wet bulb. I'm going to say that's about 19. I've got to get it moistened first here. But this is my dry bulb. Well, maybe I'll turn it this way so you can read it. I'm using Celsius on this side here. And so let's see. That's reading, I mean, here it would be 18 and there's 20. So that's about 19 for our dry bulb. Let me put a little, let me get that wet just a little bit. Okay, for my wet bulb. If I don't make a mess out of everything. Right away that was almost 18. Okay, so we had 19 and 18. Dry bulb was 19. I'll just put 19 dry. Wet was 18. Okay, to start. Okay, and then let me just do the, oh, I'm getting water everywhere. Do this for a little bit because I'm trying to facilitate the evaporation process here. So I'm going to spin this for a little bit, right? And it says if the air is saturated, 100% relative humidity, then both thermometers read the same temperature. So that meant none of the water vapor was able to come off of my gauze. None of the water was able to evaporate off of my gauze into the atmosphere. If that temperature of my wet bulb didn't move very much, okay, that would mean that they were saturated. Both thermometers read the same kind of temperature there, or the temperatures don't move, kind of thing. All right, let's see if that's enough. Usually got to do it for a minute or so to kind of give it a chance to evaporate a little bit. Okay, hopefully that won't go flying off. Okay, so my wet bulb, let's see if we can read that. Let's see, there's 16. That's about 16 for my wet bulb. Dry bulb stayed at 19, so my wet bulb actually went down to 16, so it did cool just a little bit. So we went from 19 down to 16, so really that's a 3, okay, degree change. And then we have some tables that will help us figure out what the relative humidity is. So in this scenario, dry bulb minus wet bulb, so the 19 minus the 16, okay, dry bulb temperature minus wet bulb temperature across the top, we had a difference of 3 degrees Celsius. And now along this column, this is what your dry bulb was. So if my dry bulb was 19, well, they don't have a 19 in there. Well, let's pretend it's 18. And we were to go down by 3, a difference of 3, the depression. That would mean that we would have a 72% relative humidity in the room today. Across the top is the wet bulb depression, you know, what that difference was between dry bulb and wet bulb. We had a difference of 3. And so, I don't have a 19 on here for dry bulb, but we'll go with the 20 there. So anywhere from 18 to 20, one of those in there, 72 or 74%, since I don't have, well, let's go with a 73%, since I don't have a 19 on my table. But that would be between the 72 and the 74% relative humidity. And so this is the method that we use. We've got our tables that we can use. can very accurately help us get the relative humidity of the atmosphere. So today about not too bad, about a 72, 73% relative humidity day, not bad. But if those temperatures were the same, right, you would have saturated air. That meant that the water on the gauze couldn't even evaporate into the atmosphere. The atmosphere was saturated, so you'd have 100% relative humidity if your wet bulb and your dry bulb temperatures were the same. Okay, so and didn't change at all in there, no matter how much you spin that around. So that was one way. That's called a psychrometer or a sling psychrometer, they call that. And I think they'll have a nice picture of one. But yeah, so here you have some gauze on one bulb, and the other one is the dry bulb. So wet bulb and dry bulb, and yeah, they got a big one there that they can really sling around. A sling psychrometer, they call that. A very good way to translate those into relative humidity. Another way they talk about, so another one is a hair hygrometer. Maybe some of you are familiar with this. Your hair is actually a very good detector of humidity, right? The moist air, your hair kind of wants to expand, and when it's dry, it'll kind of shrivel up a little bit. But they actually do make, using hair, human hair or horse hair sometimes, but a hair hygrometer, that it gets attached to a needle that can move as the hair expands or the hair contracts. It'll move like a little needle, and then it can tell you about relative humidity. So some of us already know, yeah, oh, it's a very humid day because our hair just like wants to frizz out. So yeah, that's a good thing on also trying to detect the relative humidity percentages. Some ways we measure humidity. Okay. All right, let's see. Adiabatic heating and cooling. So these processes are extremely, extremely important in the atmosphere. And so let's talk about these processes. These adiabatic processes are temperature changes that occur due to a change in pressure. So rising or sinking air is what we talk about in an adiabatic temperature change. So the motion of air molecules kind of increases when air is compressed. So let's say we're got an air parcel and it is sinking. It is getting closer to Earth's atmosphere. Remember how gravity is pressing in? Gravity is greatest at the Earth's surface. And so there's most densely compacted of the gas molecules there, right, at the Earth's surface. That's where we've got the greatest air pressure. You remember that from the last chapter? When air is compressed, right, that motion of the air molecules, you're compacting the air molecules together, they're bumping back and forth into each other. That's actually going to cause air to warm when it's compressed. We call that compressional warming. Try to keep those two terms together when we think about the atmosphere. Compressional warming, those molecules are bouncing together, bumping off of each other. So descending air is compressed due to increasing air pressure. Remember how when we looked at the atmosphere in the vertical, that it was most dense and most pressure at the Earth's surface, where it was at about 1,013 millibars, right, or 14.7 pounds per square inch. You remember that? At the Earth's surface. So as air is descending, going down, it's going under more and more pressure, right? And so that's going to cause the air molecules to bounce off of one of each other more, and will cause warming, compressional warming. Okay. Well, on the other hand, if an air parcel is rising in the atmosphere, it's undergoing less and less pressure. So it will expand and it will cool, okay? So we call that expansional cooling. So the air will cool, rising air will expand due to decreasing air pressure as you go up in the atmosphere. So expansional cooling. So these are some temperature changes. They're called adiabatic temperature changes that are due to changes in pressure, okay? As you either descend, greater pressure, or ascend, rise, with less pressure. Compressional warming and expansional cooling. We think about these adiabatic heating and cooling processes. These are extremely important in the atmosphere. Okay, so these adiabatic temperature changes when air expands or when it compresses. Okay, yeah, so when it rises, it's definitely going to expand and cool. When it sinks, it's going to compress and warm. Keep those two things in mind. Okay, so the rates that it's going to warm or cool, we talk about adiabatic rates. So the dry adiabatic rate, this is when you have unsaturated air, right? Less than 100% relative humidity. Unsaturated, we call that. 100% relative humidity is saturated. Well, this is referring to unsaturated air, okay? Less than 100%. The rising air will expand and cool at 1 degree Celsius per 100 meters. Or you might think of it as 10 degrees Celsius per 1,000 meters, okay? And I more or less like it in the metric and with Celsius, but they do give it in, Fahrenheit and feet. So 5.5 degrees Fahrenheit per 1,000 feet. Or this 1 degree Celsius per 100 meters, or we can say 10 degrees Celsius per 1,000 meters. I think our picture is going to do it like that. So the rising air will actually cool if it's unsaturated. Okay, it will cool at that dry adiabatic rate. So for every 1,000 meters that it goes up, that it rises, it will cool 10 degrees Celsius for every 1,000 meters. Unsaturated air. A descending air is going to compress at that same rate. So 10 degrees Celsius per 1,000 meters or 1 degree Celsius per 100 meters, however you want to look at that there. Descending air will compress and warm at that same rate. This is known as the dry adiabatic rate because we're not at saturation. Okay, dry air, we would say, or unsaturated air. That's the normal kind of dry rate. Well, the wet rate, it's a little bit slower. You are getting the cooling, but it's a little bit slower. The reason being, this starts to happen, the wet adiabatic rate, when you get to your condensation level. So here we've got a parcel of air that is rising through the atmosphere. As it continues to rise, at some point it is going to cool enough where it reaches its saturation point, right? It has cooled so much that, well, content equals capacity, and we have 100% relative humidity. We've reached saturation, okay? We cool that any bit more. We continue to rise just a little bit. Remember, condensation is going to happen. The air is at capacity. It cannot hold any more water vapor, and so it begins to condense out, right? That's that condensation level, the saturation point, 100% relative humidity, our dew point, basically. And so now, yes, air has reached the dew point. Condensation is occurring. Well, remember, condensation releases 600 calories of latent heat, right? Latent heat of condensation back into the environment. And so it's sort of warming the environment just a little bit. So it offsets the cooling rate. Okay, so that latent heat of condensation is going to throw off our little adiabatic cooling rate, right, to the wet rate. And it's less than, and it will vary a little bit, but we'll keep it kind of simple to where we'll think about 0.5 degrees Celsius per 100 meters. So not quite as much as the dry rate, which was 1 degree Celsius per 100 meters. Now it's only cooling. It's cooling, but only now at about 0.5 degrees Celsius per 100 meters, and that's the wet adiabatic rate. And it's slightly less due to the liberation of those 600 calories, right, per gram of condensation that's happening, right? That water vapor going back to a liquid, we're releasing so a little bit of heat energy. So that offsets that cooling rate, and it slows the cooling rate just a little bit. So that rate does vary, but we'll try to keep it simple. and we'll say about 0.5 degrees Celsius per 100 meters is your wet adiabatic cooling rate. So yeah, the air parcel of the air is going to be lifted into the atmosphere. It will expand and cool. It's going to reach that condensation, right, level, and then continue to rise. Beyond that, you're going to get even cooler temperatures, and you're going to start to get condensation. That's actually going to be where you would start to see clouds forming. The bases of your clouds would be at that condensation level there. Okay, so it's going to continue to cool, but it will just kind of be a little less than your dry rate, since that you are releasing a little bit of that latent heat from the condensation that's happening. Okay, so remember your processes there. That 600 grams is going to get released, and so that'll offset it just a little bit of the cooling rate. Still going to cool, but not quite as rapidly as the dry rate. So let's take a look at that scenario here. I don't know how well you're seeing that, but we've got the surface right here, and then this is the height in meters going up. We've got 1,000, 2,000, 3,000, on up to 5,000 feet in the atmosphere. And off of here, they're talking about the cooling rates, the dry rate here, and then once we get past that condensation level, it will go and cool at the wet adiabatic rate. So let's take a look. We start with a parcel of air at Earth's surface at 32 degrees Celsius. So if that's going to cool at the dry rate, it would be cooling 10 degrees Celsius for every 1,000 meters, the dry rate, right? Okay, so here we go. 1,000 meters, we've cooled off 10 degrees. So now we're at 22 degrees Celsius. We go up another 1,000 feet, another 10 degrees, 12 degrees Celsius. Well, we get right here at 3,000 feet, we've cooled to 2 degrees Celsius. This happens to be, okay, the capacity, content is equal capacity for that particular air parcel, and so this is where condensation would begin. This is the saturation point, 100% relative humidity right here. And notice you've seen the clouds forming. The bases of the clouds are right there at that condensation level. Clouds are liquid water droplets, and sometimes ice crystals too, depending on temperature. So we're at 2 degrees Celsius here. Well, it continues to rise, okay? And so as it cools, now it's only going to be cooling 5 degrees Celsius per 1,000 meters at the wet adiabatic rate. A little bit slower. It's at the wet rate. And so from here, where it's 2 degrees Celsius, we go up 1,000. It'll be at -3 degrees Celsius by the time it hits 4,000 meters. You go up another 1,000 meters to 5,000, it's going to cool off an additional 5 to a -8 degrees Celsius. And so now it is still cooling, but it's cooling at a little bit slower rate, the wet adiabatic rate, we would say. And that's because it's slightly offset by that release of the latent heat due to the condensation that's happening. And we see our clouds in there as well forming right there at that condensation level. That's basically the dew point there, right? Okay, so that's just sort of showing you the adiabatic cooling of the rising air, dry adiabatic rate versus wet adiabatic rate, right? Dry is when it's unsaturated, and wet is when it has become saturated. Cool, but it'll cool a little bit more slowly. Okay, well, how are we getting the air to actually rise in the atmosphere? There's certain scenarios that we can think about here. One way, okay, these adiabatic pressure changes in here is orographic lifting. This is due to an imposing mountain barrier that forces the air to rise. Okay, so air's coming along. Let's say a scenario coming off the east or the west coast of the United States. We have the Pacific Ocean out there, that nice moist air coming off the Pacific Ocean. Well, we have some imposing mountain ranges. First you get the little coast ranges, and then you get the huge Sierra Nevada mountain range. That air is going to be forced up. Going to be forced to rise. And so when air rises, it expands, it cools, right? It will cool to the Condensation point, the saturation point, 100% relative humidity, it's going to form the clouds. You're going to get the precipitation. It's going to rain out on that windward side of the mountain range, right? Acting as a barrier there, forcing the air to rise. It's going to rain out on the windward side. Well, that air is going to come down, right? We rained out on the windward side. It's going to come down the leeward side of the mountain range. And as it's coming down, it's undergoing compressional warming. And that is going to warm at that dry adiabatic rate. It's going to warm. Compressional, right? Warming as air descends. And so that's going to dry up any clouds that you might have. It's going to lower your relative humidity, dry up your clouds, and we can get some expanses of areas that are called rain shadow deserts. I think we've mentioned these before when we talked about some of our deserts, the rain shadow deserts. But here we are, moist air being forced to rise. It's going to expand and cool, hit the dew point. We're going to get all the rain, the clouds and the rains out on that windward side. The air's going to come down, descend, sinking air, compressional warming, and then you've got this on the leeward side. So on the other side, this is the leeward side, here's your windward side, leeward side of the mountain range, you've got a desert scenario happening because that compressional warming is going to want to dry up any type of moisture. And so you can get these rain shadow deserts, we call those. We've mentioned those before, the rain shadow deserts. Okay, now, so that's one thing, having an imposing kind of elevated terrain acting as barriers, forcing air to rise. Something else very common here in the Monticello area or in Arkansas in general, kind of during the spring, usually our chance for rain is going to be caused by this frontal wedging. Okay, frontal wedging is when you have a wedge of cool air. Cool air is much more dense, right? And it's going to wedge under, and the warm air is going to want to rise up over that wedge of cold air. So that cool air acts as a barrier to warm air. It's much heavier and sinking there, and then that warm air is going to want to rise right up over it, and they call that frontal wedging, part of fronts. And we'll have more to say about fronts, but fronts are part of storm systems called mid-latitude cyclones. Cyclones are a counterclockwise rotating thunderstorm, type of a shell, air mass cell happening in there. So this is basically here in the springtime in Arkansas. If you're going to get rain, it's due to this frontal wedging, where the cool air is wedged beneath and the warm air is forced to rise. And so yeah, that's a way of getting air to be lifted. But yeah, these are called mid-latitude cyclones, we call those. Another way we can get air to rise, a scenario off over, see if I can find my map, where air is getting kind of converging together, being kind of forced to come together. Well, it actually can't go down into the land when the air gets forced together, so it rises. And so we see this out over, it's very common, out over the peninsula of Florida. So the air is coming off the Atlantic Ocean, it's coming off the Gulf of Mexico, and it converges, and it will converge up. It will cause that air to rise. So convergence of air, causing it to rise and forcing it to lift. And you see, I mean, daily pop-up thunderstorms over Florida because of that convergence, that lift in the atmosphere. That's another one, the convergence. Low pressure, and it creates a low pressure under there, and the air rises. Another scenario, localized convective lifting. So say on a clear kind of summer day, by about mid-morning or so, the day was started out in the morning, clear, no clouds to be found, but you can get this sort of localized heating of the surface which causes a little pocket of rising air. So you get a little pocket of rising air, and it creates these little puffy cumulus clouds, kind of mid-morning to late into the afternoon. You see these little localized convective lifting, where unequal surface heating causes little pockets of air to rise, and of course warmer air is going to be buoyant and it's going to want to rise, and so you'll see those little puffy kind of cumulus clouds. We'll be talking about our various types of clouds, but these little cumulus clouds usually start forming late morning on an otherwise clear summer day. You're just a localized kind of unequal heating of the surface. Little pockets of air will want to rise, and you'll get your beautiful little kind of fair weather puffy cumulus clouds, we call those. So on an otherwise, clear kind of summer day. So there's some pictures again of the various processes that are going to get the air to rise and lift the air. This was the orographic lifting of a mountain barrier coming along, hits that imposing elevation, and the air's forced to rise, right? Frontal wedging. Okay, so you've got this cold, very dense air wedges in under, and the warm air is going to want to rise and lift above that. Here you've got the converging winds, right? And they've got the peninsula of Florida, and the converging air, well, it can't go down into the ground, so it will go up into the atmosphere with convergence. Localized convective lifting, and so here they've got, the sun's really warming different, kind of unequal patches there, and you will get a surge of warm air rising, and it'll create, once it gets high enough there, it'll create these little cumulus clouds, these puffy, white puffy clouds, the cumulus clouds. These are kind of our fair weather clouds. They're not going to be producing the precipitation. Okay, those are some ways we can get air to actually rise in the atmosphere. Okay, stability of air. Okay, so the tendency of air to resist vertical motion or displacement or to continue to kind of rise has to do with the stability of the air. Very stable air is going to want to resist any vertical displacement. So it's always going to be, the little air parcels always going to be cooler than the surrounding air. So if it's cooler than the surrounding air, it's always going to want to sink. It's just going to want to stay and resist lifting. It's denser than the surrounding air, and it's always going to want to sink. So that's kind of stable air. No adiabatic cooling is happening because it's neutral. It's kind of not moving. It's stable. So absolute stability occurs when the environmental lapse rate is less than the wet adiabatic lapse rate. So the air parcel is always cooler than your environment, basically. So it's going to want to continue to resist any rising motion. Absolute kind of stability in there. And you might get some little widespread clouds, very little vertical thickness. If you get any precipitation at all, it's very light to moderate with a stable type of air mass. Now, on the other hand, if you have an unstable air mass, something we call absolute instability, it's completely unstable. It acts like a hot air balloon. It's always going to be warmer than the surrounding air, and it's just going to want to rise in the atmosphere, right? So rising air, it's going to be warmer than the surrounding air, okay? It's always going to want to be rising. It's less dense than the surrounding air. Continues to rise until it hits an altitude with the same temperature, and then it would become neutral, but it's always going to want to rise because it's warmer than the surrounding environment. So instability in the atmosphere occurs when the rising air is warmer than the surrounding air. Just like a hot air balloon, it's just going to want to keep rising. So kind of two scenarios there. One that's very, very stable. It's always cooler than the surrounding air, that's stability. One that's unstable or instable, they say, that's always warmer than the surrounding air, and it's going to want to continue to rise. Kind of two scenarios, opposites there. Absolute instability, adiabatic cooling, of course, because it's going to want to rise, so you are going to get expansional kind of cooling happening with that. The environmental lapse rate is greater than the dry adiabatic rate, so again, the parcel is always warmer than the surrounding atmosphere, and so it continues to kind of rise, and so you can get clouds that are often towering. I mean, these are called our cumulonimbus clouds or our thunderstorm clouds. So in an absolute unstable environment, yeah, you're getting towering clouds forming, and these are huge, great vertical development of your clouds, and that's these cumulonimbus clouds, and we'll talk about our cloud classifications in a second. You're getting towering cumulonimbus clouds, these are the ones that are thunderstorm clouds, the lightning, the hail. Some of these can produce some tornadoes out of those. So yeah, unstable air definitely wants to continue rising. Then you get something we call conditional instability. So for that is when the atmosphere is stable for unsaturated air. It's stable for dry air, okay? But when you reach the point that it becomes saturated, it becomes unstable, right? So it's stable for unsaturated air, but unstable for saturated air. So for a while it's stable because it's still unsaturated, but then it reaches that saturation point and becomes unstable. So a conditional instability, and I think we'll have a picture of some of that, I think, as we're doing. So this first one is absolute instability. So all the way as the parcel of air is going up, it's rising, and it's always a little bit warmer than the atmosphere. So here it's coming along, rising. The air is 2 degrees warmer, right, than the environment. Here we go, we're 4 degrees warmer. We're 10 degrees warmer. We're 18 degrees warmer. So our parcel just continues to rise, and that's really, you are going to get some very towering kind of cumulonimbus types of air parcels happening out of that, and clouds out of that. Absolute instability. Conditional instability, that one that we kind of talked about, well, here the rising air is about 1 degree cooler, so that's very stable. Its tendency is not wanting to rise. Here the rising air is 2 degrees cooler, okay, still fairly stable. But up here it reaches that condensation level, it becomes saturated now, and so now the rising air is warmer, okay, than the atmosphere, and continues to be warmer, about 4 degrees warmer. Here we're 7 degrees warmer. So it was stable for unsaturated air, and it became unstable with saturated air. So that's sort of a conditional instability scenario. Okay, but warm air is always going to want to, if it's warmer than your environment air, it's going to want to continue to rise. So, okay. So the stability of air does determine, vary to a large degree, the type of clouds that are going to develop, as well as the intensity of the precipitation. So I already kind of talked about how that convectional kind of localized heating gave us our nice puffy cumulus clouds on an otherwise clear day. Those are kind of like our fair weather little clouds. They're not going to produce any precipitation from those. But those cumulonimbus clouds, so that absolute instability in the atmosphere, you're getting those towering, vertically developed cumulonimbus clouds. There you're going to get your thunderstorms, your lightning, your hail even out of some of those. So yeah, to a large degree, the type of clouds that are going to develop are due to the stability of the air. Okay, so we are going to look a little bit at some of that. Condensation and cloud formation. So let's just reiterate here. I don't know if you can see my little notes I wrote there, but for condensation to happen, we need 3 things. We need water vapor, right? We got to have the water vapor content. we've got to have our air reach the dew point. It's got to cool down enough that we reach saturation. We got to have the dew point, right? And then for condensation to actually happen, we got to have those CCNs, those cloud condensation nuclei. So those little solid particulate matter, the soot, the pollen, the dust, right, in the atmosphere. So clouds are actually very dirty. They need that dust in there, those little particulate matter in there for the water vapor to condense on. Okay, and so we needed those three things: water vapor, we need to reach our dew point, and we need the cloud condensation nuclei for condensation to happen. So water vapor in the air changes from a liquid, changes to a liquid, and we form dew, maybe some fog. The little cloud particles will form. We'll get some clouds happening. So water vapor requires a surface to condense on, as I mentioned. Possible condensation surfaces on the ground might be the grass, right? You wake up in the morning and you see a little dew out on the grass. A car window, yeah, you might get some dew on that, but it needs something to condense on. Condensation surfaces in the air, again, little tiny bits of particulate matter, those little solid aerosols. These are called, and here they're finally giving you the term, condensation nuclei, or cloud condensation nuclei, or CCN. I abbreviate those. So dust, little smoke particles, soot, ocean salt crystals, the sea spray, that kind of thing. Pollen, another one, little particulate matter for the water vapor to condense on. We do need those. Condensation nuclei, we call those. So clouds are actually millions and millions of these little minute, little tiny water droplets, or they could be ice crystals, little tiny ice crystals, just depending on how cold your cloud is, how far up in the atmosphere and how cold it is. They might be tiny ice crystals as well. And we classify our clouds on a couple of things. Kind of their shape, so their form is one way we classify them. And there are three basic forms. This first one is called cirrus. And cirrus are very white, kind of thin looking. They're actually made of ice crystals, your cirrus clouds. They're very thin and wispy. They kind of look like a little feathery paintbrush stroke, the cirrus clouds. And these happen to happen way up high altitude where it's very cold so that you can get the ice crystals. But that's a cirrus cloud, thin, kind of wispy white clouds. The cumulus clouds, these are globular, clumpy, almost kind of look like cotton ball kind of masses, but globular cloud masses often associated with fair weather. So I mentioned our fair weather cumulus clouds, these little clumpy, puffy clouds, cumulus clouds. So globular. So we're looking at shapes here. Stratus, so stratus are sheet-like. We've talked about the strata in the landforms, right? The stratigraphy. But this is sort of sheet-like, the layering look to them. So sheets are layers that cover much of the sky are our stratus clouds. Okay, so three forms: cirrus, globular, or cumulus, and stratus. Okay, form. And they may have some pictures of some of these as well. There's your cirrus clouds. So very thin, wispy, almost like a little paintbrush stroke, formed of ice crystals, right? So these would be very high clouds, thin and wispy, very beautiful clouds, the cirrus clouds. Then they've got what we call the altostratus. So stratus in that they are sheet-like, kind of covering the sky, but alto, that term alto is a mid-level. Middle is sort of alto. You have your sopranos, you have your bass, you have your alto, kind of medium range in there. So mid-level clouds, but they're layered. So an altostratus cloud. And then the cumulus, the clumpy, kind of globular ones, like a little puffy cotton ball. We like to look at the different shapes that the cumulus clouds will form and change into. That's a fun thing to do, to see what the shapes look like. Cumulus clouds, puffy kind of clouds. So form or shape is kind of one way we classify them. The other one is based on the height, so what the altitude is, where they're found, okay, based on the height. So we do have high clouds above 6,000 meters. These would include, of course, the cirrus clouds. The cirrus clouds are high clouds because they're made of ice crystals. Your cirrus clouds are. Cirrostratus, so they're thin and wispy and high clouds, but they're layered, okay? And a cirrocumulus, so a high, thin, wispy, kind of clumpy, right? Cumulus or globular shape to them, okay? Those are all high clouds. Here, middle, okay? So a lot of times you are going to see that term, that prefix of alto for the middle clouds. 2,000 to 6,000 meters are the alto range. Mid-level clouds, so altostratus, altocumulus, so stratus would be mid-level layered, okay, sheets or layers. Altocumulus, mid-level cumulus clouds, okay. Low clouds would be below 2,000 meters. For these, of course, you can have stratus, so low-level lying sheets or layers of cloud. Stratocumulus, so layered but cumulus shaped, a low lying in that. Nimbostratus, so the nimbo stands for rain cloud, stratus kind of layered. So your nimbostratus is typically a rain cloud. Nimbo means rain cloud, right? Nimbus means rainy. But kind of depending just how far up your nimbus cloud is, if your temperatures are cold enough, you might actually get snow out of nimbostratus clouds. It just depends on what your temperature is. If your temperature is below freezing, you would be getting snow out of a nimbostratus cloud. Just depends on what your temperature is. But most of the time we think of the nimbostratus, just that low line, just kind of gray, covering the sky, and that showery kind of precipitation, rain happening. We think of the nimbostratus, but if that was cold enough, you could actually be getting snow out of a nimbostratus cloud. These are your main ones. So we've got sort of height and we've got shape, right, coming together to form classifications for our clouds. And then we have this category in here that these are of great vertical development, the towering cumulonimbus clouds, okay? And so cumulo, right, so they are globular in shape. They are towering. Nimbus, because yeah, we're getting rain out of these. In fact, these are thunderstorm clouds. They're towering to such great heights that we are getting the lightning. Of course, the thunder and the lightning go together. They produce rain showers, thunderstorms. You can get hail out of this time. We'll look at the hail development in a minute. Occasionally, tornadoes will come out of these cumulonimbus clouds. So lightning and thunder are associated with the cumulonimbus cloud. These are your thunderstorm clouds, basically. Okay, so according to height, yeah, we've got our low clouds, so sort of hovering, they're gray kind of clouds, layered, the nimbostratus, the stratus, right? The nimbo is going to be giving you your rain. Middle clouds, we've got, the altocumulus clouds there. And then the high clouds, we've got a little bit, they're showing the cirrocumulus clouds. So cirro, they're kind of thin and wispy, but yet they're clumpy in shape. They're very high clouds because our cirrus clouds are made of ice crystals. Okay, keep that in mind. And here's another one, kind of showing many of them here next to each other. There's that cumulonimbus cloud, that big anvil head, right? You got all the lightning and the thunder and the rain coming from that thunderstorm cloud. cumulonimbus cloud, thunderstorm cloud there. Yeah, cumulus, just our little puffy, fair weather clouds, that localized kind of convective heating happening. The cirrus clouds, the cirrostratus, the layers of those, altostratus, mid-level, stratocumulus, so low-lying, kind of layered but cumulus, yeah. So a lot of classification, kind of combining shape and elevation or height for our classification of our clouds. Okay, fog. Well, fog is basically a cloud that is at the Earth's surface, right? So it's condensed material, condensation material that is at a level that is impeding in our visibility. So fog is considered an atmospheric hazard because it reduces our visibility. Okay, so it's condensation, sort of a cloud, but it's at the ground level. Okay, its cloud base is at or very near the ground, the Earth's surface. So most fogs form because of radiational cooling. When we have movement of air over a cold surface, so we can get that radiational cooling. Is so like on a clear night, all that terrestrial kind of radiation is trying to make its way out to space, and when we have a clear night, radiational cooling can cool the ground down. So then we can get movement of air, sort of evection of air, warm air in over that cold surface, and that can create enough cooling of the air that we do reach saturation, 100% humidity, right? And condensation can start right near the ground surface. And so that's kind of where the fog is coming from. And so the types of fogs, we've got here one called, these are fogs caused by cooling, evection fog. We kind of have some famous evection fog, but this is where warm, moist air moves over a cool surface. And so I know we've talked about the Gulf Stream before when we talked about our ocean currents. The Gulf Stream, right, starting out off over here, wheedling its way up in the Atlantic Ocean. We do have a warm Gulf Stream, if you remember that. It actually makes its way, continues on over to the British Isles, London, England. You think how foggy London is. They even have the London Fog Company because of the raincoats, right? That foggy, misty, rainy kind of environment there. So the London fog, right, is coming because of the warm Gulf Stream bringing warm air, but then that goes over the cooler continent, right? Warm air advecting over the cool surface here, and we get that advection fog for the London fog. From coming off of that Gulf, that warm Gulf Stream current is how that's happening, right? So they have the London Fog Raincoat, that famous company. They are famous for their fog, their advection fog there in London. That's one way. Radiation fog, so the Earth's surface cools so rapidly, forms during a cool, clear, really calm night, so you're not really getting any wind with this, but the Earth's surface is rapidly cooling. That radiational cooling cools off the surface real rapidly, and then you can get some condensation right near the surface there. That's another way. Another cooling way we can get this upslope fog. So humid air kind of moving upslope, right? This is an adiabatic cooling process. You're going upslope, you're going to get the expansional cooling, and then you can get the condensation happening kind of low levels. So upslope, but still at a point where it's going to impede our visibility. So fog, we would call it an upslope fog. These are all fogs caused by cooling. Then we have some evaporation fogs we talk about. Maybe you've seen this one, a steam fog. So with a steam fog, we have cool air that's moving over a warm water body. So out there at Weevil Pond, I don't know, towards autumn or so, where you've got sort of still some warm water. The water hasn't really cooled off very much, but you've got cool air settling in over that warm water. Remember, the water is going to want to cool off more slowly than the environment. So yeah, you'll still have a little bit warm water, and then cool air will come in over that, and you can get steam fog. It almost looks like the water is steaming, a steaming appearance to it. That's called steam fog. Frontal fog or precipitation fog. So this forms during frontal wedging, where that warm air is going to be forced to kind of go over the colder air. This happens during fronts, so cold fronts sort of thing. The rain is evaporating to form the fog, okay, and that's known as a frontal fog or precipitation type of a fog. So frontal wedging, you can get that towards the surface with that. So it's different types of fog, so pretty much where the base of your cloud is near or at the ground surface, yeah, and can impede our visibility. It can be quite a hazardous, very difficult to try to travel through them. So our cloud droplets, so they are very, very small. They're less than 20 micrometers, so 0.02 of a millimeter, very, very small in diameter. Of course, these are going to fall incredibly slow. There's a couple scenarios, a cold cloud versus a warm cloud, on how the precipitation might form. Here they are referring to the cold cloud formation, sort of the ice crystal process. The temperature in the cloud is below freezing, so it's a pretty high elevation cloud. Everything's frozen to start with. Those ice crystals can actually be a solid particulate for water vapor to condense on. So yeah, it collects the water vapor. Your little ice crystal grows larger and larger snowflakes. When they get heavy enough, they will fall to the ground, or they could actually melt on the way down and become rain. So they might start out as ice particles, snow particles, but then as the temperature changes, they may melt and come to the ground as rain. They call that the sort of the cold cloud formation of precipitation. That could be one scenario we might have. The other one, a warm cloud. This one's called collision coalition process. So basically happening in warm clouds, but you have very large kind of hygroscopic condensation nuclei. So nuclei, little particulate matter that attracts the water, vapor. So you're able to condense some large droplets forming with this method. Kind of various sizes of droplets in there, and those larger droplets are colliding with the smaller droplets, and so they're becoming larger as they go during their descent down along the way. So kind of two formations. One's kind of a cold cloud formation. This would be the collision coalescence method with a warm cloud, okay, where you're starting out with some getting larger and larger droplets, liquid water, okay, is another method. So kind of there's the technicality on what's a rain droplet and what's a drizzle droplet. Either way, you're going to get wet, right? But the rain droplets have at least a 0.5 millimeter, like half a millimeter diameter. Drizzle, well, less than a half a 5 millimeter or 0.5 millimeter diameter. So there's just a little size difference there, but again, you're going to get wet in either case. But rain versus drizzle. Snow, these are ice crystals or aggregates of the ice crystals, so our beautiful snowflakes. Now sleet and glaze. Glaze is also known as freezing rain. So there is a little difference of scenario of if you're going to get sleet or if you're going to get freezing rain or this glaze that they're talking about. So let's take a look at your book. They've got some scenarios of what you're going to get depending on what's happening in your atmosphere. So this is sort of some winter precipitation they're talking about. I don't know, I hope that shows up pretty good. This is out of your book, page 385, figure 12.29 out of chapter 12. Okay, so we've got some scenarios here where our temperature, this little dashed line here, our temperature here below here is less than 0 degrees Celsius, so less than 32 degrees, so that's like the freezing temperature. Less than 32 here, I'm sorry, greater than 32 here, less than 32 up there. So we would definitely have freezing above there, where you see kind of the blue colors there. Okay, so if you've got, you know, your cold cloud way up there, right, it might produce the snow, but once it comes through this warm layer, you've got a very thick warm layer here, well, those snow flakes end up melting and it comes down and hits the surface as rain. Okay, well, coming through here, we're starting out snow. We actually melt the snow and it becomes rain, right? But it's sort of, you know, kind of a thinner, kind of cooler mass of cold air right near the surface, but it's not very thick. So this rain didn't have a chance to really freeze on the way down because that's such a thin layer of cold air. So when that hits the surface, of course the surface is below freezing, it will freeze on contact. That is known as freezing rain, and it just leaves a glaze, a coating over everything, over your, you know, your electricity wires, the tree branches just get coated in the freezing rain. So on contact, it freezes. So it was a thinner wedge of cold air in there. That would give you the freezing rain. Well, over here, look how thick that cold air layer is. That's a thick layer of cold air. So here we go. We got the snow coming along. It kind of goes through a warm wedge here, and it melts into some raindrops. But those raindrops come down, and they have a thick enough layer of cold air coming in close to the surface here that it actually, those rain droplets will refreeze into little pellets. And so those would come and hit the surface, and they actually bounce. That's sleet, okay? So the raindrops will actually refreeze before they hit the surface. So they're frozen already, and they will bounce, and that's sleet. So that's really kind of a difference between the layer of cold air. This is pretty thin, a shallow freezing layer. This is a large or a deep freezing layer. You're going to get your sleet out of that scenario. And then, of course, if it's, you know, making snow, and then this is a below freezing all the way down, right? You're going to get snow scenario out of that. No melting had occurred in that scenario. So that's sort of your scenarios for some precipitation that can occur. So whether it's rain, or whether you get the freezing rain, freeze on contact, or whether you get the sleet, freezes before it actually hits the ground, little pellets, or, you know, does it not freeze at all and it stays as a snowflake all the way down. So kind of that difference between sleet. Sleet is forming, it's going to pass through a warm layer, okay, that's producing some rain, but then, you know, it gets to the point that it's cold enough to refreeze that, and it'll freeze before it hits the ground. That's kind of how you're going to get your sleet. You need to have a kind of a thick, cool layer in there, sub-freezing kind of layer near the ground to produce that sleet. Okay, so there you've got the warm air lying over the colder air, but it's a thick layer of cold air, and that rain will freeze as it falls through that thick sub-freezing layer. The glaze or the freezing rain, right, it's going to impact with the surface, any solid surface, and it's going to freeze on contact, you know, when you have a sub-freezing surface, right? But that layer was too shallow for it to actually freeze before it hits the ground. Okay. Hail, a very interesting kind of pattern here for our hail. I think I had a picture of that as well. What can happen in those cumulonimbus clouds? And so those large, tall, towering clouds. Got a picture here, page 386, figure 12.31. So here's our cumulonimbus cloud, right? Those towering clouds. You can actually have those go in many elevations to where at one point, maybe this lower part of your cloud is warm enough to be liquid water, right? Droplets. but that very upper part of the cloud might be cold enough to be freezing. And so in a thunderstorm cloud, a cumulonimbus cloud, you're getting a very strong updraft, okay, that's forcing that liquid water up into that freezing layer. And that will cause a little pellet of ice, right? A little droplet of ice. And then that falls back down in the warmer area and it gets bounced back up and it creates another layer, right? You get the warmer water, you bounce back up and you freeze, you come back down, get another layer of water on there, back up and freeze, and back and forth and back and forth. They're getting jostled all around. The hail is. And so you get layer after layer after layer after layer of rings of ice that are forming, and to the point that it gets so heavy that that updraft can no longer support it, and then it falls down. You get some large hail, small hail in there, the rain, the heavy rain kind of thing. With that downdraft, it becomes so heavy it can't support it in the updraft any longer, and you can get the hail out of that. And some of that hail, you know, the baseball-sized hail can get very large softball-sized hail as well. It can be very damaging to crops, to people's vehicles. I mean, hit you on the head kind of thing too. So it can be quite dangerous, right? The concentric shells of frozen water, right? So ice in there from 1 to 5 centimeters. I thought I had one where it was like the record. I don't know. Let me see. What was the record? 8 inches in diameter and 18.6 inches in circumference, the whole thing here. This was from South Dakota. That was a whopper. The world's largest hailstone from Vivian, South Dakota. 1.9 pounds, almost 2 pounds. The hit you on the head. Yeah, that wouldn't feel too good. So these can get quite large. Yeah, so these do often form in cumulonimbus clouds, our thunderstorm clouds. And so up and down, violent updrafts and downdrafts, layers of freezing rain caught in the updraft and the downdrafts of the clouds. The pellets fall to the ground when they become too heavy and they will fall out. Okay, let's see here. Rime. So rime just forms on cold surfaces, freezing of supercooled fog or little cloud droplets, and sometimes you'll see the rime. Oh, here was a beautiful picture of some of the rime. Little delicate ice crystals that form supercooled fog or little cloud droplets freeze on contact with objects, and so kind of see the wind direction there blowing those, but that's kind of some rime. So various scenarios of some precipitation that we can get. And then how we measure some of our precipitation, I think, is the last little bit here. Yeah, so rain, the easiest form kind of to measure a rain gauge. You've got a funnel kind of to collect your conduit, kind of conduct it down into a cylindrical measuring tube, and that measures in, you know, centimeters or inches. A lot of them will be in inches here in the United States, and can kind of tell you how many inches of rain. So there's a little standard rain gauge, your measuring scale on there, and keep track of your precipitation. Then for snow, there's actually a couple measurements of that. One, the depth. So you can just stick, say, a ruler or a yardstick or something like that in there and get the snow depth, right? How many feet or inches of snow. And then there's something we call the water equivalent. And so what would that equal to if we melted the snow? So what would be the water equivalent? So there's a general ratio, very general ratio, where 10 snow units converts into 1 water unit. And so say maybe you had 10 inches of snow would melt down to 1 inch of water. So it's a 10 to 1 kind of ratio that we talk about, just depending on whatever unit you're kind of using. But that is a water equivalent. kind of varies widely, but radar is also used to measure the rate of rainfall. I mean, that's just revolutionized meteorology, the radar has for intensity, duration, direction. Radar tells us so many things about precipitation, so being able to measure it and track it as well. So that is a lot about the water portion of the atmosphere and how important it is in kind of completing our hydrologic cycle. So we're getting the water vapor going up into the atmosphere, condensing back out, right, in various forms of precipitation as we saw there. So kind of continuing that hydrologic cycle and the importance of water in the Earth system, right? So precipitation, cloud formation, stability of air, the adiabatic processes, very, very important processes in the atmosphere. And so in the next chapter, chapter 13, we will look at the atmosphere in motion. We kind of looked at the motion in the vertical, but we're also going to be looking at that in the horizontal with varying air pressure. And so we'll continue our look at the atmosphere in chapter 13. So I will see you next time. Thank you.